Zinta also. Oh, okay. I'm sorry, I had a problem with my computer. It's interrupted for a while. The burning embers are illustrating risk with a set of colors which have well-defined definitions, which I cannot explore here, but which are described in review papers about these embers, of which the reference are at the bottom of this slide. And the aim is to illustrate how risk increases with some metric of hazard, which is in general global mean surface temperature. I have problem changing slides, sorry. Yes. What we want to do here is to use this framework to assemble or regroup the risk assessment from the three last IPCC special reports, which are the report on the global warming of 1.5 degrees, the report on climate change and land, and the report on ocean and cryosphere. Altogether, these reports present in themselves about 50 burning amber diagrams, so illustrate a risk for about 50 systems or integrative risks. And what we did here is to start from the source data in the report to assemble this risk in a way that is fully homogenized. A specific difficulty that I have to mention is that for the ocean related risks, these were assessed with respect to sea surface temperature. I mean the temperature of the water only in oceans. So to compare that to risk related to land systems, one that to convert the temperature of oceans to a temperature, an equivalent, a temperature that occurs at the same time for the global mean over the entire planet. And that was done for the first time in the ocean report with two vertical axes, as I show here on the figure. This implied a multiplication factor of 1.44 from one temperature axis to the others. And so what we want to do here is to apply that rule to the previous report, the report on the global warming of 1.5, because that was not done in that report yet. The rule was decided by the IPCC after the report and never applied consistently to all embers. So that's part of what we have done here. And then, of course, the intention with that is to present all these embers in synthesis figures and try to learn from that. And in particular, try to learn why some systems are more at risk than others. For each of the 50 systems, we have explanation in the IPCC report as to what they relate, as to why risk is increasing at a given temperature level. We group that in tables and then try to produce different figures, of which this is an example. The principle is that the temperature is increasing from the center, which relate to 0.5 degrees above pre-industrial, to the edge of this figure, to the exterior of this figure. So this is global mean surface temperature again. And the different systems are placed in groups depending on what they relate to. So that, for example, you have food systems, embers grouped in the left of this figure and ocean systems on the right. And each of them is placed at the position that represents its the global mean temperature at which the IPCC assessment says that the risk is becoming high. So this is the change from the yellow color to the red color in the burning embers figure. It's where the risk is becoming high. And the last step with such synthesis figure is, as I briefly mentioned, to try to identify the common properties of these systems, particularly at risk. Here, I limited the below to risks that are below 1.5 or become high risk. Okay, I finished that in 30 seconds. So we have tentatively identified a few causes for high risk, which are the fact that risk are higher in certain regions, that risk are more tightly linked to physical aspect, to physical change, that there are compound effects such as mixing, warming, acidification, etc., that some species have limited adaptation capacity, and finally that socio-economic factors also play a role. This is also summarized in this conclusion slide, which is my last slide. And the final remarks I would like to provide is the last bullet here. I would like to remind that there is
I'm sorry, but
okay.
We have to move on since you can. There is, of course, then more time in the discussion room about.
Okay, thank you.
Yeah. Okay, the next speaker is Rene Orth, so please keep it to 3 minutes. And there's, of course, then time for discussion in the outbreak rooms. Rene?
Yes.
Okay.
Can you see my screen and
go
hear
ahead.
me?
Yes.
Cool. Thanks a lot. Yes, my name is Rene Out. I'm leading an immunota research group at the Max Planck Institute for Biogeochemistry. And I want to show our work on contrasting biophysical and societal impacts of weather extremes that I've done with these nice collaborators. And so we're shifting focus a bit here to show some empirical research and empirical extreme weather impacts. The motivation for this was that we noticed that there's a lack of empirical research looking at extreme event impacts across sectors and across event types. So in a multi-hazard, multi-sector fashion. So we did that looking at 5 different sectors. You can see biophysical sectors and socioeconomic sectors here. And 5 hazards, 5 weather extremes. We look across Europe and a 15-year time frame, and at national scale, basically we identify when these hazards occur and what are their impacts in these 5 sectors that we consider here. And then if we put things together, this is a summary of the results that we find. For the first sector, for example, photosynthesis, we find that droughts and floods are most relevant in Europe. For crop yields, also droughts and floods, but also the 2 temperature extremes, heat and frost, are very relevant. For mortality, it's the temperature extremes, as is well known from the literature. And then you can see this divide here as we move from the biophysical to the socioeconomic sectors. You can see a different pattern here. For the socioeconomic sectors, it's mostly windstorms and floods, which are most relevant, while heat waves and even more so droughts are really not so relevant at all. So this approach allows to determine which extreme event and which hazard is relevant across which sectors. Now, if we move one step further and we isolate the attention response here, and we compare the societal attention with the average impact of each event type across all the other 4 sectors, then that's what we find. We see basically that storms and floods receive more attention than what would be expected by their mean impact across the other sectors. And on the other end of the spectrum, we see drought receives surprisingly little attention given its significant impact across the other sectors. Last teaser of our results that I want to show here is looking into compound events and how the impacts change for compound events. Here on the left, we identify the main compound event that occurs across Europe, which is a joint occurrence of heat waves and droughts. All the other events don't really occur jointly. And if we look into
an end, please.
Yes, if we look into how the impacts change, you can see most of the bars are pointing upwards, which basically says that if these events occur in a compound fashion, we see amplified impacts across sectors. And that's my summary. So we can, with this approach, we can see these impact signatures of different types of extremes. We see this clear divide between biophysical sectors and socioeconomic sectors. And attention on droughts is surprisingly low given the significant overall impacts. I don't have time to cover the caveats, but maybe we can come back to this in the discussion. If you're interested in further details, we just published this last month. Thank you.
Okay, yeah, thank you very much. The next speaker is Lina Dorado.
Hi, good morning, everyone.
Hi.
I'm Carolina Herrera. I'll be presenting on behalf of Engineer Lina Dorado. So, share my screen. I'm not available to share my screen.
No.
Okay, so I'll be talking about the Risk Atlas of Colombia. This is a very important instrument for us for risk disaster management. With this atlas, this was born from the need of advance in risk knowledge in national and regional levels. And with this instrument, this seeks to improve the understanding of this of disaster risk in the dimension of hazard, exposure, and vulnerability, and taking into account the environmental characteristics of the territories at national and regional scale. So the justification for this work is based on the question of what happens when we make the decision-making process based only on hazard information. So in this slide, we see the National Seismic Hazard Map of Colombia. This is defined in the Colombian Seismic Design and Construction Code. This map divides the country in 3 levels: high, level, intermediate, and low seismic hazard. And if we ask a question of what happens if we select, for example, one city, for example, Cali, we can see from the map that this has a high hazard level. Likewise, there are exposed elements like people, housing, schools, hospitals, and these infrastructure components may be affected during the occurrence of an earthquake. However, it is important to consider and ask a question of what happens with the physical vulnerability of these exposed elements. There may be cases where the houses have been built in an informal way without meeting the requirements established in the seismic design code. And on the other hand, we have another cases where the houses have been constructed meeting all of the requirements of the building code. So with this context, it is very important to identify and recognize that the vulnerability, the physical vulnerability of the exposed elements is very important to take into account for the decision-making process. So therefore, in the event of the same seismic event, the expected losses in these 2 kinds of exposed elements may vary in a very important way. So that's why the objective of this tool of the Risk Atlas of Colombia is to make the decision-making process based on risk parameters. So this is what I'll be talking about later in the session.
Okay, thank you very much. So the next presenter is Kornhuber.
Yeah, hi everybody. I think you need to stop sharing the screen. Yeah, perfect.
Yeah.
Hello, thanks for organizing this. This is really a fun event so far. So I'll talk about multiple breadbasket failures in CMIP6 and the GGCMI project and how they're going to change in the future. So this is essentially what I'm doing. And just to kind of give an overview, so the breadbaskets are essentially those regions that produce a major amount of crops in the northern hemispheres. And yeah, naturally, when you have several extremes happening, causing multiple harvest failures, then this is a societal issue and can lead to social unrest. There are certain jet stream patterns that cause simultaneous extremes, and they indeed affect regional crop production. But so far, we haven't really assessed how this will change in the future. There are a lot of uncertainties with respect to the circulation, but also some issues with modeling crop. And this is essentially what we're looking at here. And we look at the future risk of the multiple breadbasket failures determined by covariability of crop production across those regions outlined in this graphic above, looking at CMIP6 and GGCMI and comparing that to those results from the FAO harvests and ERA 5 with such a covariability matrix. And this essentially looks at states where the jet stream is strongly meandering and those where it is normal. The bright red colors on the left-hand side here show you that the harvests and the breadbaskets do co-vary strongly whenever we have these high amplitude jet states, and they don't really whenever the jet is a bit more zonal. And in the middle and on the right side, you see that this response is really underestimated by CMIP6 and also doesn't really change much in future. And one major source of this underestimation or this bias is that there's essentially no strong surface response in these models. So we identify a major source of extreme weather biases. Essentially, during those meandering jet states, the extreme weather response is missing in CMIP6, and it also doesn't change much in future, although we see an amplified dynamic
Can you
component.
come to the end?
That's the end.
Please. Okay, thank you. The next presentation is by Marlies Barendrecht. Can you stop sharing?
Yeah.
Oh, thank you.
Yeah, I hope you can see my screen. So
Yes.
I'm going to talk about drought-to-flood events, something that I'm studying together with some colleagues. So first, some examples of why is this important. So what drought-to-flood events, we are talking about droughts that are ended or followed within a short time frame by a flood. And as you can see, so there are some cases, for example, in case of droughts leading to wildfires, which then, when there's a flood, can actually lead to a lot of mudslides. Or in some cases, because there was a drought and the soil is dry, this actually reduces the impacts of the flood because the water can be absorbed by the soil. Or in case of Texas, for example, where pumping of groundwater led to subsidence, the pumping of groundwater because of drought conditions led to subsidence, which then increases the flood risk because the land is lower. And so these are some examples of why it is actually important to study these events as they happen, well, as one system and as one event, instead of looking at droughts or floods separately, which is a lot is known about these events separately, but not a lot of research is being done on these drought-to-flood events. And this is what we are working on within the Perfect Storm project. And particularly, I'm looking at how can we model the interactions between humans and droughts and floods? So human adaptation and how does it influence these events? And what we are working on now is we are doing a case analysis of drought-to-flood events so far 170 cases across the world, but it's a work in process. As you can see, we haven't included the European cases yet. And we are looking at gray literature, newspaper articles, scientific literature to identify the hydrological drivers, adaptation measures, and impacts that are that were present in these cases. And ultimately, what we want to know is, what variables and components do we need to put into a model to model systems that are experiencing these drought-to-flood events? And can we use one model to basically model the dynamics of all these systems, or do we need different models depending on the system characteristics? If you're interested, I have some preliminary results to share, and I would also very much like to discuss your points of view on this.
Okay, thank you very much. The next presentation is by Lisa Thalheimer.
Good morning, everyone. Let me just share my screen real quick.
Yes.
All right, perfect. So today in my session, I would like to talk about assessing the nature of systemic risk and compound vulnerabilities. And this is work together with Franziska Gaup at PIC EAT Forum and Christian Webersig in Norway at the University of Agder. And specifically, we're looking into a country case study in Somalia, where we know obviously there's a lot going on in terms of poverty, in terms of extreme weather events, and just to showcase you the kind of compounding vulnerabilities, what the country is affected by, I listed these in the couple of icons you can see at the bottom. And there's also the locust crisis going on and also a lot of internal displacement. And this is kind of our motivation to better understand what's happening on the ground. How can we model that? And how can we essentially come up with effective policy interventions in this case? So we're using a systemic risk impact pathway model, which looks a bit, overwhelming at first, but in my session, I would really like to dive deeper into one spotlight on environmental vulnerabilities. And I highlighted these, there you go. They're the big bubbles. The spotlight on environmental vulnerabilities in my session. And with that, I would like you to join my session and invite you for a discussion. Thank you.
Okay, thank you very much. So the last presenter is Ashish Manoj.
Yeah, am I audible? Hello, could somebody confirm?
Yes.
Cool.
Can you share? I still see the plaque now.
Okay.
Now you can go ahead.
Yeah, so my name is Ashish. My today's talk is titled Disentangling Soil Moisture and Precipitation Coupling over India from a Compound Flood Risk Assessment Perspective. Before I begin, I would like to acknowledge my collaborators for this present work. So coming to the motivation of this study, essentially we look at preconditioned compound events. By definition, they are events in which an underlying weather-driven condition or a climate-driven condition increases the impact of an hazard. The importance of soil moisture in moderating flood characteristics is still not well understood in the tropics. We make use of an event coincidence analysis, which is essentially an event-based approach to identify and investigate the spatiotemporal patterns of soil moisture and precipitation dependence. The datasets that we use are the GPM IMERS product for precipitation and GLDAS 2.2 version product for soil moisture. So essentially, to a brief overview of the analysis, we essentially convert the time series into event series. And firstly, we make use of the tail dependence from extreme value theory to get a first estimate of the probabilistic conditional probability. And then we move on to event coincidence analysis and essentially calculates the coincidence rates between these two time series. So we identify regions where we feel that soil moisture and precipitation attain their extreme states more together, and this can lead to higher flash flood risk. So these are the results for at the annual time scale, and we can see some significant clusters occurring in the different major river basins of the country. And again, we repeated the analysis for 4 temporal windows, and we can see that due to anthropogenic climate change or LULC changes, there is a significant change in the clusters due to catchment degradation or to the changing precipitation patterns. So we also evaluated the timing of coincidences of these S&P coincidences over India. So that's it. I'd like to keep it short, and I would like to invite you to the breakout session for more details. Yeah, that's it from my side. Thank you.
Okay, thank you very much. Thank you for all the presentations. And so now we start the breakout room. So the room 1 is impact metrics. Then we are going to have Philippe Marbaix